IEEE AP MTT Society chapter in association with the IEEE Bangalore section. It is our second endeavor with respect to this webinar talk. And today we have a very young professional who is really young. And just to mention you that he is so young that he got his latest Young Scientist Award in last couple of months back. And that is his third award I came to know from some other source. So hopefully we are looking forward to very exciting talk from him. And to apprise Dr. Devdeep Sarkar that we have very good registrations. It is more than 300 and very senior people from the professional industry has registered, and most of the participants they are from the professional background, almost 60 to 70% what I could go through. And so you can understand the level of interest that people are showing in our webinar talk, and that is thanks to our chair, Mr. Punit, and our Chengappa and our full team who is working behind this scene. So with this small introduction, and I also thank the Mr. Dr. Shantil Kumar, who is the chair for this APMTT joint chapter of Bangalore section, for encouraging us in organizing this talk. And now I request Kirti Priya to formally introduce the speaker of the day. Thank you.
Thank you, Dr. Chandrakant. Good evening to all the participants. I'm very happy to introduce our speaker today, Dr. Devdeep Sarkar. Dr. Sarkar is currently an assistant professor in Department of Electrical Engineering, IIT Ropar. He completed his BE in Jadavpur University and got his MTech and PhD from IIT Kanpur. Dr. Sarkar has worked as visiting researcher and postdoctoral fellow in Royal Military College of Canada. His current research interests include design of MIMO antennas for 5G and beyond, wireless channel modeling, EM for biomedical applications, and IoT. Dr. Sarkar has authored and co-authored more than 30 peer-reviewed journal papers and more than 50 international and national conference papers. He serves as a regular reviewer in journals such as the IEEE Transactions on Antennas and Propagation, IEEE Antennas and Wireless Propagation Letters, Antennas and Propagation Magazine, and IEEE Access. He is also serving as associate editor in IEEE Access since December 2019. Recently, one more feather has been added to his cap. He has been selected for the Young Scientist Award in the URSA General Assembly, which is a prestigious global community for radio science. Hearty congratulations to you, sir, from the Bangalore section side. And on that note, I welcome you to deliver the lecture, sir. Over to you now. Thank you.
Thank you. Thanks, Kirtipriya. Thanks, Dr. Chandrakant. So I hope you all can hear me. I am Devdeep Sarkar. And first of all, I would like to thank the entire IEEE MTT Bangalore chapter and the IEEE Bangalore section for organizing this particular webinar. So as you can see from the title of my talk today, that is 5G Massive MIMO I have kept there. So 5G MIMO, Massive MIMO, all of these things are currently in the present age. These are very, very popular, or we can say that these are the buzzwords. So the students and academic researchers and industry personnel, so everyone is looking to pitch their projects or products, whether it may be some new design or whether it's some algorithm. So everything is somehow like they try to put in the context of this 5G. And the research areas in 5G definitely spans very wide areas of the engineering and science. In particular, if I talk about the electronic side, so there is input from the VLSI, input from the signal processing, communication networks, and radio frequency integrated circuits and antennas. So it's quite natural that it's not possible to cover all the aspects in 1 hour. So for this webinar, which is I would like to focus on mostly the electromagnetic aspects. So by electromagnetic aspects of this 5G massive MIMO, I mean that I will talk about the antenna design part a little bit. I will also focus on how the correlation between various antenna elements can have some critical role in the wireless channel modeling, and some of the new topics or new techniques that we have introduced. So I will come into those parts later. But before I go into or dive into the technical part of my lecture, so I'll just have a small glimpse of the two institutes that I just show that I'm associated with. So currently, I am an assistant professor in the Department of Electrical Engineering, IIT Ropar. It's pretty new, like 2008. It has been established, and you can have some glimpses of its beautiful campus. But before joining here, I worked as a postdoctoral fellow in the Royal Military College of Canada. So it's a very old institute and established in 1876, like you can imagine. So it's basically a military college. So there I was fortunate enough to be associated with Professor Yahya Antar, who is a IEEE Life Fellow, and mostly the research part that I will be talking about at the end of my lecture is funded from the Canadian researcher grant that he gets. So just to acknowledge that. So now I will go into the main agenda of my presentation today. So first of all, I would, as I mentioned about the 5G and the MIMO. So my objective is to discuss that why this MIMO or this multiple input, multiple output systems are so critical in the context of this fifth generation wireless communication network. So G is standing for generation, as we all at this point probably know. So to just introduce that aspect, I have just tried to present a particular slide that has the contrast. Like you can look into what we have now, that is a present day smartphone staying in this 2020, and looking back 80 years back, we had these to communicate wirelessly. It was mostly in the military grade portable AM or FM radios. So the contrast is huge, and it has been a very fascinating journey, one can say. But the question that arises here is that whether this military grade radio, which is probably used in the time of the World War, so whether that has any category in terms of these G, 1G, 2G, whether we are can classify it in that way. So the answer is probably no, because it's a military application. So we would be looking in terms of the civilian side. So we can say that the first commercial mobile telephone service, or MTS, has been like it came to the fore in 1946, and some people are calling it 0G. And then, but we are mostly interested in terms of the portable cellular phones, because the earlier thing that I discussed, the mobile telephone system, it is basically used for the intra-vehicular kind of communication. Some trucks carrying essential goods and they want to communicate on the way, that kind of thing. But from a personal point of view, a user point of view, this first portable cellular phone that is probably designed by the Motorola, you can see a picture of a businessman using that. So, and it started, and we can show a particular infographic that is basically mapping all these travel from the 1G to the 5G. So you can see that there are stages, like the research and standardization is there, and then we are going to have the commercialization of this kind of technology. So what is driving us in this journey? One of the crucial thing is, initially it started by simply communication of the voice data or the audio, you can say. But later on, people wanted to push more and more data into the system, and the applications or the systems became more and more data hungry. So that actually had a lot of research and lot of thought process went into the design, and a lot of industries put their foot on there. So we went from the 2G to 3G, and now we are talking about 4G to 5G. So one critical aspect is we want to increase the data rate, we want to increase the system capacity, and for that purpose, what is a crucial resource, we can say. So the resource is definitely the wireless spectrum. So what we mean by exactly the wireless spectrum is that we are trying to communicate from, say, one user to a base station, or one user to another user via some intermediate node. So basically we are launching the signal in terms of the electromagnetic waves, or some baseband data we are mapping into some carriers that have a certain frequency, and we have certain kind of operational bandwidth there. So we need to look into two things. One is that how much data we can push in, or the I am talking in very crude terms, so that might not be very technically okay, but I am trying to convince, like most of the people who might not be, who can be of different diverse background. So the idea is that we can increase the capacity or the data rate, and the second point is we have to think about the coverage part also. So you can see that from this infographic that once we increase the operation frequency, or we go in the higher range, so then we need to only mostly think about the capacity, because for the coverage we need to operate at the lower frequency range. So here then people are from the context of the 5G, people talk about the sub 6 gigahertz 5G and sub millimeter wave 5G, or some application they go for the vehicle technology application above 100 gigahertz or stuff like that. So the point is, whether 5G is only about the data rate, I think that point has to be addressed, is that uh, 5G has various things under its umbrella. So there are three major themes. One, we are talking about the enhanced mobile broadband. That is actually having the extreme data rate or extreme capacity, those kind of aspects. But other aspects are, say, mission critical control, or by that we mean ultra reliable low latency communication, URLLC people talk about. So latency as low as 1 millisecond. And then another point is the massive internet of things, or IoT, as that is another buzzword at the present. So all these things are falling in the 5G umbrella, but for this particular talk, we will be mostly looking into the data rate aspects and not cover all those parts. So there is also the concept of 5G hyper service cube, where we can think about in terms of the delay and the throughput and the links in the three axis, and can actually encompass all the other things, like there should be some kind of backward compatibility. Now, since we are talking in the Indian context, I think it is very important to address that part. So Department of Telecommunication of Indian government have put forward a lot of effort on this 5G testbed project, and that is you can find the details from the web page in the IIC. So various institute, the IIC and other IITs and several other institutes and industry people have joined hands in this kind of project. So the developments for that can be found in this link. So just trivia here. So now coming to our main point, that why we need the multiple input, multiple output kind of system. So the idea is that we have shown that there is a equal importance of the wireless spectrum, and there are some approved spectrum for the 5G and the sub 6 or sub millimeter wave frequency range. But another aspect is also that we cannot increase the transmit power levels beyond a certain limit, because there are safety requirements and we need to move towards the greener and safer communication. Now but we are again, there are several applications, those are that are data hungry, so we need to increase the data rate. So in simple terms, that if we have some kind of constraint on the available spectrum, and we have some constraint on the power levels or the signal to noise ratio that we can ensure in a particular system, then we can use multiple antennas and some associated signal processing in that to enhance the data rate. So it is basically, you can say, an interdisciplinary kind of thing, that we need to think about the antenna and heavily depend on the signal processing and the communication protocols. But here I will mostly talk about the antenna part. So just a brief schematic of this multiple input, multiple output system, that we have an input data and we have this transmitter module. So between the transmitter module and this receiver module, we have the wireless channel. So how this channel is actually getting like modeled. So in our case, if we have, say, multiple antennas, more than one antennas at the transmit and more than one antenna at the recipient, so the channel can be modeled as a matrix. And this channel, that though the transmit module or receive module, that they can be in the line of sight, they cannot be in the line of sight. So if they are not in that case, we might have several scatterers in between, we might have some reflecting surfaces. So there will be a lot of multipath. And if the multipath fading is there, that can be modeled in terms of the relay, modeled in terms of Rician. There are various ways to do that. But the idea is that we are going to have this, we are going to tap into this multipath faded signal and then use that in our benefit to enhance the data rate. So there is some theory, like we can, without going to too much of mathematical details, that we can talk about the channel capacity for a single input, single output, which is SISO, you can say, or the MIMO, and the MIMO, that is the multiple input, multiple output. So the channel capacity for a single input, single output, we know from the undergraduate level or maybe the pre-graduate level, from the Shannon's capacity theorem, that it is dependent on the bandwidth. So I am basically this quantity that I am showing here for so I am talking in terms of the per bandwidth. So its unit is bits per second per hertz. So mostly there is that term PT upon sigma n square, which is basically signifying the signal to noise ratio at the transmitter end. So we have the channel response there modeled by a scalar as H. So once, as I mentioned, that we have multiple antennas involved, intuitively you can think that we have the channel not as a scalar but as a matrix. So once we have the channel matrix, then we can do some information theoretic analysis and we can find out the possible like error-free data rate kind of thing. So which we define in terms of the SU-MIMO here. So the point is that we can show that if we have a certain enhancement in the rank of this matrix, then we can get enhancement in the data rate without increasing the power or the bandwidth level. Or well, we can also say that we can slightly tone down the power and we can still get high data rate. So those kind of issues are available in the literature, but I will not go into that mathematical details. So instead of that, I will take another approach to explain the basic concepts, two things in this MIMO for handset and the base station. So I will focus on the diversity and the beamforming before coming to the details of the massive MIMO. So let's take a step back and we can think that for the first generation system, we did not have multiple antennas. I am now thinking about the handsets. So then the handsets in the first generation system, we can just see a simple sleep dipole kind of arrangement is being made to communicate. And sleep dipole, we all know that that can be designed by using simply protruding the inner coaxial cable and using the sleep from the outer conductor to get a very balanced omnidirectional kind of radiation pattern. All those things are there. But whether if we have multiple antennas in our handset, that is happening in the present fourth generation, or we can say in the fifth generation also. So there, what is actually happening is we can think about it in terms of the receive diversity. So just look into this figure that I have shown for the receive diversity, that we have the transmitter that is basically emanating signals, and we are basically having the multipaths that are appearing on the ports of the receiver antenna. So since we have two receiver antenna here, so we can now combine them by using some maximum ratio combining or some switch diversity scheme. All those things are there, but the idea is that we are basically using these multipath components or these weighted components in an intelligent way to enhance the information rate, or we are effectively increasing the data rate as compared to the single input single output system. So what is the way to, that we can ensure that this will actually give us some benefit? Whether we can put any number of antennas in the receiver and get an enhancement in the data rate or any kind of arrangement, the answer is no. We need to check some of the things. What are those things? That we have the main antenna, and with the diversity antenna that has to be located at a specific distance from the main antenna. Specific distance, by that we do not always mean the physical distance. It can be in terms of the electrical distance. And the idea is that we need to have the signal appearing at the ports of these two antennas in an uncorrelated fashion. So spatial diversity, by placing the two antennas, the main antenna and the diversity antenna at certain spacing in terms of the wavelength, we can achieve a spatial diversity. So that will give us the enhancement. Another way, if we suppose we do not have the luxury of placing the antennas far apart, then we can also use that scheme of polarization diversity. So in the right side of my slide, you can observe that we have the polarization diversity with a horizontally polarized and a vertically polarized antenna. And once because we have these orthogonally polarized signals, so they will interact with each other very less. So we can essentially tap into the uncorrelated signals from there. So spatial diversity, polarization diversity, they are used in our handsets. And right now, if you look into the integrated 4G, 5G handset antennas, a lot of research is actually going on, and many of my colleagues or junior friends who are doing PhD or masters are working in this particular problem. So there, the idea is to increase the number of antennas in the particular handset. And if we have, if we can ensure that these ports of the antenna or the signal arriving at these antenna ports are very much uncorrelated, then we can ensure that we will have some kind of enhancement in the data rate. So interested people can look into this kind of papers. I have just cited a paper from Dr. Chow Desmond Sim's group. But now I am slightly digressing from the main topic, that I am talking about the handset. So what will happen, what is happening in terms of the base station antennas? So next, I have just tried to look into to understand the evolution of the base station antennas that will eventually culminate into the massive MIMO which we have at the present. So I have prepared a basic review of the base station antennas for mobile communications. So from the C. Beckman and Lindmark. So these interested people can also look into this paper. So base station antennas typically, if we talk about 2G or 3G context, so they are 1 to 2 meter of height with gains of 15 to 20 dBi and placed in towers between say 25 to 75 meter above the ground, and the power handling capacity is there. But key things are that we have to ensure the sectorial coverage, the operational frequency depending on the particular application that can be tuned. So that can be in the GSM 900 to 1800 or some other multi-band things. But a key thing that I would like to focus here is the diversity that I was discussing in terms of the handset that was already there in the base station kind of processing. So to combat the fading, because intuitively you can think that not only the base station is communicating with the user will also communicate with the base station and send out some signals. So the base station also has to do some kind of channel acquisition and those kind of things. So the diversity is very important there. So how those things are taken care of, like whether we can go with the omnidirectional for the coverage thing. The most intuitive thing is the using the omnidirectional antenna. But again, we need to think about enhancing the gain or basically tuning the patterns. So people thought about using sectorial coverage by using, say, these reflector back dipoles. You can see in the second figure. And there are ways to optimize the beam width of this coverage and three sector kind of things as I have shown here. But the diversity part, to handle that, the one useful way is to use the dual polarized elements. So I have just shown a schematic that dual polarized elements can be used to ensure that polarization diversity in the base station. But apart from that, when we think about in the downlink context, then we have to think that the base station has to have the beam that is being radiated from an antenna perspective, the beam that is radiated from the base station to contact with the user equipment, that has to have some kind of like we need to have some dynamic control over that. So first thing is, instead of using static kind of beams, we may think that we can introduce the variable phase shifter. So that kind of change was done when we moved from 2G to 3G, and that will include some variable electrical tilt. So in which direction? Next question arises, in which direction? So from basic antenna perspective, we know that there we can talk about in terms of the elevation, we can talk about in terms of the azimuth. So the idea is, initially there were fixed beam antennas, but slowly we needed to move into ways that we can say tune the elevation. So along the elevation direction means along the, as in the earlier figure I showed, that from the Z axis we can basically tune the beam along the vertical direction. So vertical tilt is there. Now if we put more number of arrays side by side and we can ensure very good port to port isolation, then we are actually moving into the direction that we are having spatial diversity there. Alongside that, we can tilt the beams that is radiated from the base station by some, say, remote actuator, remote electrical tilt kind of thing is can be there. But still, the figure that I am showing here is ensuring only tilt along the elevation direction. So if we want to ensure overall kind of additional azimuth beam forming and steering capabilities, we can introduce some beam former over there. An active adjustment to the amplitude and phase distribution can be controlled by the beamformer unit, and traditional remote electrical tilt configuration can be kept for the vertical tilt, but we can have the horizontal tilt also. So I am just coming to the concept of the full dimensional beamforming. That is a very key thing while designing the massive MIMO kind of systems, is that we need to have the beamforming in terms of the elevation as well as the azimuth. So next thing I talk about is that whether, previous slide I discussed that whether we are using these beamformers. So instead of using the beamformers, if we, the ultimate case for the massive MIMO or that kind of thing, which people may think of, is we can have a dedicated transceiver to be integrated directly with each antenna element for the maximum amplitude or phase control of the aperture. But again, there are other aspects in the design like economic aspects, manufacturability, weight and heat management. So these will be has to be considered once we go into a practical design. But the idea is that we have a large number of elements and dual polarized elements, mind you. that dual polarized elements for the polarization diversity and spaced at a particular electrical distance, so that the coupling between the ports is also very less in for those transceivers. Now we want to have an independent control of all of them at the same time, so we can have a say complete dynamic control of the amplitude and phase in the aperture. So once we achieve that, the vision for that is just to show the contrast from the typical 4G base station to this 5G massive MIMO kind of base station, is that we are going to have the elevation vertical beamforming as well as the azimuth beamforming, and that can also provide some fixed directional links to some user equipment from where the nodes can communicate with the base station with very less power. So the power handling capability of the base station will also be better, that we might not need that much of power that we needed for the 4G sector. So essentially we will be moving towards the linear communication. But here I would like to just to complete the discussion on the inception of Massive MIMO. I'd like to discuss that whether there is some kind of relation with the MIMO, like this beamforming and the MIMO concept that I discussed previously. So the relation in terms of electromagnetic perspective can be derived in terms of the fact that from singular user MIMO to a multiple user MIMO, we are actually looking into this beamforming, because when we have the when we are using in the multi-user MIMO, we are basically using the at the same time and frequency resources, but spatially these various devices are decoupled. But in the case of a single user MIMO, we are actually individually we are serving each of the devices. So single user MIMO, people say that it is good for peak user data rate, but multi-user MIMO is actually good for the system capacity. So now the thing is, what about massive MIMO? Whether we can connect from there, we can definitely. So we can say that the massive MIMO is an extreme case of this concept of multi-user MIMO, and you can follow the book of Bjornsson or follow his lectures to just get an idea that how the conventional multi-user MIMO and the massive MIMO are different. So main thing is that the number of base station antennas that can be very high, that will be very high in fact for the massive MIMO system, and we need to work with the time division duplex mode and the link quality. So the fact that we have a large number of antennas, that will actually lead to a phenomenon known as the channel hardening. So almost there will be no variations over the time and frequency, and we can achieve the good channel acquisition in massive MIMO systems by based on simple uplink pilots and exploit the channel reciprocity. So that part, this uplink pilot or whether the uplink massive MIMO channel modeling, I will touch upon in the end of my presentation. But before going into that, all the things that I discussed, like the description of a say generic massive MIMO system, this can be little confusing. So it's better to just understand a proper massive MIMO antenna architecture. So in this part of my presentation, I decided to focus on a case study. So first, let us notice that there are several testbed kind of things available. I have just cited one of them, that actually if you see the real life antennas that are involved, so there is this Lund University, the LU-MIMI, that is called so massive MIMO testbed in the Lund University. So that is basically having more than I think of the order of 100 antennas. So the idea is that you can see the hierarchical architecture that is coming there. So at the front end we have an array of antennas, but at the back end we have the switches and software defined radios to ensure this control processing, then the centralized processing, then distributed processing, and to the overall array of antennas. But the design here is fairly simple, and you can see the amount of signal processing at the back end, that is also significantly high. So one way that people are trying to think is that what should be the optimum geometry or optimum topological arrangement of these various massive MIMO elements. So to just focus on that, I decided to discuss about a stacked patch antenna geometry, because that will lead some insight into what goes into a massive MIMO antenna design. So this paper, actually stacked patch antenna with dual polarization and low mutual coupling, this is published in Transactions in 2016. So this is a very good starting point in my opinion, because we can actually touch upon all the aspects that I discussed previously in terms of the dual polarization, in terms of the possible beams, or in the various like controls of the beams, highly directional beams in various directions that will ensure the full coverage. So all those aspects, and finally the mutual coupling also. So I will come into those parts one by one. So you can see that the stacked patch geometry is actually having, they are describing in terms of the 7 layers. So the bottom layer is actually the feed network. I hope that everything is visible from the slide. So the feed network is there, and we are actually showing the 2 ports, port 1 and port 2. So one for the horizontal polarization, one for the vertical polarization. And to couple, the radiating patches are in the top layer, in the layer 1. And in between, why the stacking is needed, because we are using some slots, bow tie shaped slots in the ground plane, and there are these metallic coupling strips. And dielectrics are there in the layer 2, 4, 6, so I'm not discussing about them. So the idea is that we need to couple the signal or couple the energy from the bottom ports to the radiating patches. And how we get the dual polarization. So here I just a different view of the same structure. So layout on layer 7, so you can clearly see the 2 ports. Now, if you observe that when we have port 1 excited, then these 2 vertically oriented bow tie slots are actually getting excited, and then these vertically shaped bow tie slots, they are actually exciting the completely orthogonal green colored coupling strips. So then we will get a horizontally polarized radiation. So you can just visualize from the current distribution that I am showing here that when we excite the port 1, we will get the horizontal polarization, and when we excite the port 2, in a similar fashion, you can explain that we will get a vertical polarization. So dual polarization thing is being achieved by 4 antenna unit. Now question can come that why we are using 4 antennas, because we want to basically increase the gain. So I'll talk about that later. But first, I'll show that the fabricated prototype as well as the simulated prototype of the single antenna array unit. So there you can see that they have also embedded actually the S parameter response for the feeding network. So I'm not going into that. So the simulated and measured antenna S11, S21, and S2 to show that we are actually ensuring very low coupling between these 2 ports. So this is extremely essential that we reduce the coupling below minus 30 dB, so that we are actually, or minus at least minus 25 dB, so that we are having very less interference between the 2 orthogonally polarized ports. So next thing is, as we all know, that not only the S parameters, we need to think about the radiation pattern. So for the horizontally polarized radiation, they have plotted the copole and crosspole, and similarly and along the E plane. So we are just from the figure you can observe that the Z axis is actually coming out of the paper. So we need to consider the XZ and YZ planes. So one will be E plane and one will be H plane, and that thing will be flipped for the vertical polarization. But for a single antenna unit, we are having almost symmetric kind of patterns for both horizontal and vertical polarization radiation, and the peak gain is of the order of 10.5 dBi. Now, how from this antenna unit we are going into a massive MIMO configuration? First step is they are using a 4-unit sub-array. So just the unit that I have described, that is replicated 4 times. So you can see the top view and the bottom view. And now we have in total 8 ports. So we need to focus on all these reflection parameters starting from S11 to S88. And you can see that this is basically designed for the sub 6 gigahertz massive MIMO, as probably I should have mentioned this earlier. But at this point, we can show that the 3.6 to 3.8 gigahertz frequency range, basically that is the effective operating bandwidth is there. And the simulated measured results are also in certain agreement. Then we have to ensure, as I mentioned, the coupling between all these 8 ports. So they have considered the symmetry and chosen the particular S parameters that are in the consideration. So the coupling is actually also less than minus 30 dB for the various port combinations. So now the next step is to assign or to analyze the radiation pattern that is coming. So here they have only showed the measured pattern for the vertical polarization as well as the horizontal polarization. So the thing that is happening is, since the arrangement or array direction is along the X direction, so along the XZ plane, they are basically having a very narrowing of the beam width. So basically they are having a very high directivity, around 16 dBi or something. Now next step is to this particular turning torso architecture that is used for the massive MIMO. So you can identify that the 4-unit sub-array that is actually replicated 6 times at each of the stages. So there are 3 stages if you notice, A, B and C. and each of these stages they are having six sub arrays. Each sub array is having four units. So total, you can say that 72 kind of thing if we combine all of them. Now there is this progressive tilting. Like it's not that they are stacked in a like a simple way, one above another. There is some progressive twist or progressive tilting about 20 degree or so. So they have optimized that to reduce or to ensure that the coupling. There are various kind of coupling combination that can be possible in this kind of architecture. So all the coupling level have to be ensured below the minus 30 dB. So that thing once they are described in terms of experimental terms, so you can see that it is basically covering the entire azimuth, and we can also have some tilting or very high gain pattern along the elevation plane, and that will produce the desired beamforming, full dimensional beamforming that is needed for the massive MIMO kind of application. So similar kind of turning torso architecture people have used instead of patch antenna. This is done by Professor Ahmed Kishk's group, Kishk and Professor Sebok from Concordia. So they have basically used the dielectric resonator antennas for this massive MIMO system. So this is a paper from. So there are several such papers or several such designs, but this turning torso architecture is one of the critical geometry. And at present, I am working with one of my collaborators in IST Trivandrum, and some master students are involved, and we are probably trying to build a similar kind of antenna using some other elements. So once that is out, we can probably discuss on that. So anyway, we have so far discussed about the architecture. So I just touched upon the architecture part to give a real life feel about how these massive MIMO kind of antenna geometries are designed, or what are the steps that is involved, starting from the single element, ensuring the dual polarization, then making the sub array, and after the sub array we can use this kind of turning torso architecture to ensure the full coverage and the beamforming, all those parts. But the second thing is what happens, or what is actually the driving force which will ensure the optimum geometry for a specific propagation environment. Like I can have, I priori know that this will be my general distribution of my user equipments, or at these particular locations my user will be there, and they'll try to communicate between each other via the base station, or they'll try to communicate with the base station. So I talked about the turning torso architecture, that is fine, but whether there are some other kind of innovative architecture that is possible that will probably give us more benefit. So to have that kind of an insight, or in terms of the research also, what we need to do is we need to first quantify the connection between this antenna geometry or antenna orientation, antenna architecture with the channel model. So that is very important, that we need to see the link between the complete wireless channel with the antenna interactions. So if you remember that I discussed in the first MIMO slide that there was, these antennas were talking to each other, there was some correlation between the antennas. So that actually can deterministically affect the complete wireless channel. So we are working on some of the techniques on that. So this will be the final part of my webinar, where before going into the details, just a little bit of recap. And this picture I've taken from the popular Bjornsson book on the Massive MIMO network. So I talked about the downlink operation and how the beamforming and all those things can be done. But what happens if the user equipment is actually trying to communicate with the massive MIMO base station, and we are actually trying to configure a particular geometry that will give us the optimum performance. So to that, as I am repeating, that we need to find out some connection between the antennas and the channels. So that is done through the antenna inter-antenna correlation. So why I am saying that, because there are several other ways of channel modeling. We can use, if we talk about the deterministic channel modeling, we can use the recorded channel measurement. We can use the ray tracing technique, which is also very popular. But a simple analytical tool that people often use is the local scattering spatial correlation model. So we have these two figures are also from the same book, very popular, that 2D local scattering model and the 3D. So I can talk about the general 3D local scattering spatial correlation model. So you can see at the along the YZ plane, there are some arrangement of dots. So these dots are basically representing the antenna elements in a kind of massive MIMO configuration. So they are spaced, or they are located at a particular electrical spacing. For the time being, we can say that they are spaced at a half wavelength. So now we can say that the user is actually impinging or illuminating a planar wave, plane wave fronts, which might not be the case in the near field, but again, some assumption that that is far field. The user is in the far field for the massive MIMO base station. So now it is launching some planar wave, and that wave is actually falling upon the massive MIMO base station. So how the correlation between these various antenna elements, like side by side, we can say the MF antenna and the close by we can say a jet antenna, how these two things can be found out? So to model the correlation between two closely spaced antennas, that is fundamentally defined for the receive mode. This has to be like said at this point, that when suppose two antennas are placed nearby and we want to find out the correlation. So the idea is, basic idea is, some wave is actually falling upon the two antennas and some signal is being produced at the receive ports. So what is the correlation between these two signals? That is what we are actually trying to find out. But practically, when we try to determine this correlation, so the way we do is we find out the radiated far field components for the individual port excitation in the transmit mode. So we construct the equivalent transmit system, and then we, for the incoming wave distribution, we use some statistical angular probability distribution. And there is some cross polar discrimination factor there. So P theta, P phi, and some cross polar discrimination factor of the incoming wave is there. In that way, and to quantify the correlation, we define the term envelope correlation coefficient, ECC or rho E. So that can be found out for the two antennas 1 and 2 in terms of the radiated field through this popular equation. That is actually, if you take a uniform propagation environment with no cross polar discrimination, that becomes nothing but the vector correlation between the far field. So let's come back to the massive MIMO with that definition. So you can easily see that suppose I have 100 elements, say 10 cross 10 massive MIMO kind of like assembly. So then we will have the correlation pairs, like for every two antennas we can have we can quantify a correlation. So basically we'll have a 100 cross 100 correlation matrix. And how like if you find to go through the most of the literature, generally the equation to find out the correlation between the two antenna elements is dependent upon that incoming distribution, that is basically from the f theta phi, the term that I am showing in the equation. Another thing is the exponential term that is actually containing Rm minus RL, that is the distance between the two antenna elements. So the only key thing that people generally take for the analytical spatial correlation modeling so far is the spacing between the antenna elements and the incoming probability distribution, so which can be Gaussian, which can be anything, like depending on the Laplacian or propagation environment. But that what the key thing that is missing over here, the electromagnetic issue, is the relative polarization of the antenna elements. Because we are defining in terms of the antenna array or array factor, array factor is not the conventional array factor is not valid if we have multiple polarization elements. We can like just review the basic antenna theory, and you can see that array factor cannot be defined the way the conventional array factor is defined. It cannot be defined for a system that is having arbitrarily polarized antenna elements. But that polarization between the relative polarization of the antenna elements, that can have some very significant deterministic effect on the spatial correlation matrix, which might not be captured in the normal equation. So this was one of the main driving factors that our research, my research in RMC had, that we need to find out the proper expression for the spatial correlation of between these two nearby elements that has some contribution from the relative polarizations as well. So there, what we, but the background was that one of my collaborators, Dr. Saib Miki, was previously associated with the university in US, that he also worked with Professor Antar in RMC. So the point is, in his book or in the two papers, he introduced the term known as the cross correlation Green's function. So this is a very general term. This has no connection with the massive MIMO or anything. This just treated the like interaction between two arbitrarily polarized antennas and how to find out the correlation from the antenna currents. So that connection was actually built by this concept of cross correlation Green function. And later on, one of my other colleagues, Dr. Clausier, was with the University of Rennes in France. He also came for postdoc there. So they worked on extending this cross correlation green function to some arbitrary say arrays, but they did not put it in the context of massive MIMO. So if you are interested, you can look into these papers or the book that is also available for buying, the New Foundation for Applied Electromagnetics, spatial structure of fields. So this is a very interesting book because not only this correlation part, this has some other insight of general electromagnetic aspects of the communication systems as well. But then just a little bit of the visualization of the thing that I just mentioned, that how the cross correlation green function is connecting the current distribution and the far field correlation. So the way it works is, for any two antennas, say two half wavelength dipoles are there, we can find out for each of the port excitation, we can find out the total current distribution in between the two antennas, and we can spatially discretize the current distribution in terms of spatial samples with particular polarization. So this is basically a infinitesimal dipole array. So once we have this kind of a decomposition in terms of the infinitesimal dipole array, then we can combine the contribution due to each of these dipole pairs and we can get the total correlation. But the question again comes is how to combine? How to combine the contribution due to these two individual arbitrarily polarized elements? So the way to go about that is, there is this C bar. If you just notice the equation, instead of going very deeply into it, there is a C bar term. So this actually represents the cross correlation Green's function tensor. So why it is a tensor? Because say we have the antenna polarization X, Y, Z of one of the dipole, and the other dipole can also be X, Y, or Z. So in total, we will have 9 components. So it's better to represent the 9 components. If we had 3 components, we might have used the vector notation. But since there are 9 possible components, we are using the tensor notation. And this is nothing but a generalized extension of the array factor. So you can call that it as a generalized array factor. I'm not going into the detailed maths of the thing, but the idea is that instead of solving all the integrals, like if we want to solve the correlation from the fields, there are some angular integrals. But when we are using this kind of approach, the every essence of the angular integrals is being captured in this cross correlation green function. So if we can find out the green function in the proper way, then there is no need to do all those tedious kind of field based calculation, and we can fundamentally connect the antenna currents. The J1 and J2 are basically the antenna currents, so we can have some connection between the currents and the far field correlation. So my interest in the subject grew when Professor Antar visited IIT Kanpur, where I did my PhD under the supervision of Professor Kumar Vaibhav Srivastava. So there I picked up the topic of cross correlation green function and used it with FDTD for the first computation of the envelope correlation coefficient over a wide frequency band. So this was not for the massive MIMO thing. This was mostly for the two nearby elements. You can say that it's a handset or some wireless access point kind of things. So we want to characterize them over the wide frequency range. So there I used this cross correlation green function. But later on, when I went to RMC for my postdoc, so I decided that this cross correlation green function can be very helpful in solving that long-standing problem for massive MIMO, that is the local scattering model for the correlation that can be actually solved by using this CGF or correlation green function. So I would discuss, like, there are a couple of publications. One was in the transactions in last year, and another was in antenna wireless propagation letters. So if you are interested, you can go through them. But one of the things that how to estimate the eigenstructure of this correlation matrix for a dual polarized massive MIMO system, that I will briefly discuss over here. So again, I come back to the figure that we have a massive MIMO base station configuration, and we have a user equipment that is probably illuminating some signal on the base station. So now, instead of following the earlier expression that only dependent upon the earlier expression for evaluating the correlation, if you remember that only had a term, this exponential j k rm minus rl, that term was there. The spacing between the elements will definitely control the correlation. But in addition to that, we have some of the factors in terms of the tensor notation that is actually taking account of the correlation, account of the relative polarization of the antenna elements. So I have written it in the this compact tensor form, but it can be expanded in terms of the 9 components, and we can find out that what will happen. Say one antenna element is along the y direction, one antenna element is along the z direction, or one antenna element along y. After some of the elements there is an x directed element also, it could be there. So how to find out for the all the general cases? The general case is here, like we are having the complete tensor, and that will solve the general case. So we can actually use, and the antenna currents, the most simple antenna element that can be used to model the radiation from a massive MIMO base station configuration, we can use Hertzian dipoles. So that is also one critical thing, that the most of the literature in wireless communication literature, they consider the isotropic elements instead of the Hertzian dipoles. But isotropic elements are not easy to realize, and in fact if you think about from a practical design perspective, so dipoles are more general, and you can actually realize them. Small dipoles you can realize, or you can even model the radiation from any arbitrary structure in terms of a combination of small dipoles. So that is the best possible way to actually model the current in this kind of system. So just to give you some examples of the why I was talking so much about the effect of polarization and all those things, so people can think that okay, what was the problem if we just simply consider the isotropic elements. So I just show the example, because the algorithm that I developed is very general and it can be applied to any kind of arrangement. So I start with one of the interleaved arrays. So you can see that one of the elements is horizontal polarized, next element is vertically polarized. So these are Hertzian dipoles that I have taken, and the incoming signal distribution I have taken you can say two-dimensional Gaussian function. So p theta and p phi, the mathematical expression, that it is basically modeling that the beam is coming from a specific direction, so theta 0 phi 0, and it is having some spread sigma naught is basically representing that spread. So if we consider no polarization of the elements, the eigenvalue distribution of the correlation matrix will have a certain loop. That blue circle, those things are representing the eigenvalue distribution of the this like without any polarization, or if we assume that there are isotropic elements. But if we consider the polarization, we can see that it is considerably being changed. So the idea is that we are basically increased if you count the number of eigenvalues beyond a certain limit. So the dominant eigenspace is being modified for this kind of, if we use this kind of polarization. Now people solve the interleaved dual polarized arrays by some other ways also, but if we say consider a very random arrangement of this polarization, the conventional techniques are incapable of solving that, but we actually solved using our algorithm. And instead of the interleaved dual polarized arrays, we can also focus on like other kind of arrays also. But for this case, we can check that how the correlation eigenspace can be actually modified by varying the these like polarization of the elements. So there are some changes that can be seen. But another thing, the co-located dual polarized arrays, because whatever if you remember the design that I showed, that they are the two polarization elements, like for the antenna unit, if I put it, make it horizontally polarized, if I make it vertically polarized, then they are sharing the same aperture. So the idea is that we are having co-located dual polarized elements. So in that case, we can actually also similarly use the IDM-CGF approach that we proposed. So we are considering that the user equipment, just to just go back and forth, that there is a special location, and at each of the base station location there is this independently controllable ID. By ID I am meaning infinitesimal dipole, so it can be the horizontally polarized, it can be vertically polarized, and total number of elements we can count. And for each of the user equipment we can have the resulting spatial correlation matrix. In this case we are having 128 cross 128. So by simple counting of the numbers you can figure out that 8 cross 8 cross 2. So basically that is giving us this thing. So we tried to investigate that what is the effect that if we say moving the user from one location to another, like mean azimuth angle, what is the effect of that on the correlation matrix. So by azimuth angle I am meaning the quantity phi naught. So you can see, so if we found out the correlation matrix in the method that we described, then we will see that we can actually decompose the correlation matrix in terms of four components. So actually here the arrangement, as I am showing in the matrix and as I am showing in the plot, they are slightly different, because here at the lower you can say that you are basically taking a transpose of the matrix and just showing it pictorially, because the nomenclature from one is starting from the bottom left corner of the screen. So just the idea is that if you change the user location from say a location phi naught equal to 10 degree, that is more close to the x-axis, to another location phi naught equal to 70 degree, and other parameters, the theta naught and the sigma naught, all those things are we are assuming to be fixed. Then what is happening? The thing that is happening is we are actually observing that the correlation part between the horizontal antenna pairs is actually diminishing with the increase in phi naught, but relatively the correlation between the vertical pairs is actually very much dominant. So the explanation for that is lying in basic antenna or basic electromagnetic principle of this kind of dipole antenna, that we are approaching while we are changing the user location, we are basically approaching the null for the horizontally polarized elements. So now we talked about the full dimensional beamforming, or whether we can so we have to think that if the user equipment itself is moving along the elevation plane, so what is the effect of the mean elevation angle on the correlation matrix? So here we found some interesting observation that people found from realistic measurements, but there was no such explanation for that. But from this approach, this IDM-CGF approach, we found out some explanation for that also, that there is, if we change the actual elevation angle, if we increase the theta naught, then there is some contribution or some correlation between the so-called orthogonally polarized elements also, depending upon the incoming signal distribution. So this is a very interesting observation that actually matched with the realistic 3GPP kind of measurements. Another, finally, I will just at the last of my presentation, little bit about why this correlation matrix is so essential in terms of the channel modeling. Because if we there are certain techniques, this is just one of the technique that can give us a particular channel modeling or uplink channel modeling that I am talking about from the correlation matrix itself. So this part we actually presented in last year's Indian Conference on Antenna Propagation, that we can have the eigenvalue decomposition of the spatial correlation matrix. This is a very standard technique, and the diagonal matrix will contain the capital lambda. The diagonal matrix will contain the non-zero eigenvalues of the correlation matrix, and the unitary matrix U will contain the eigenvectors of R with some condition. The idea is, once we find these two things out, the U and capital lambda from the correlation matrix, then we can have some kind of Karhunen-Loeve representation of the resultant channel vector by generating various instances of random part, like the HIID is basically representing random part, and the deterministic part is actually coming from the correlation matrix. And correlation matrix, how to find out, I already discussed. So just the visualization of the channel is possible if we use that kind of thing, and just a test case with interleaved array, any kind of array is possible. This is just one test case that I am describing, that we can see that how the dual changing of the between a reference isotropic array and to a particular dual polarized array, we can basically have some kind of different kind of channels, and channel representation can be there. So once we find out the uplink channel in a proper way, then we can find out the downlink channel, and all the like the signal processing guys can take over from there, or communication guys can take over. But the antenna part, that the interaction between the antenna, especially here in this particular talk, I talked about the polarization. So that can be encompassed using that cross correlation gain function. So I am at the end of my presentation. So just to recapitulate what we discussed about the capacity enhancement, we discussed about the diversity and the beamforming techniques, both in the context of the handsets as well as in the context of the massive MIMO, a base station kind of application. And I discussed about a particular specific case of a turning torso kind of arrangement architecture of a massive MIMO geometry using microstrip patches. And then I talked about some of the algorithms that we proposed, which can actually help us to for the spatial correlation estimation of massive MIMO system for the uplink channel modeling. and we have some of the confirmation with the field test for that also. And in the for the future scopes, if there is some chance, we have some of the works on the FDTD based EM framework for massive MIMO channel modeling, and there are certain interesting application in the context of using meta surfaces or reconfigurable frequency selective surfaces to manipulate the channel space. So those things are there, and they are actually basically, you can say that we are looking beyond 5G. Some people are calling it 6G, anything. So those things are there. We have some research on that. So if there is any other opportunity that is available, maybe I will discuss. But with that, I would like to conclude this particular webinar, and I thank you all for the attention. So over to Dr. Chandrakant and Kirtipriya. Thank you.
Thank you, Dr. Devdeep Sarkar, for the nice and informative webinar.
Thank you.
I was just going through the list of the participants that I can see that continuously it is close to 150. It was, and it is still there. So that shows the people's interest in this topic. And you started from the very fundamental with some small pictures and point-to-point communication link, and then develop the massive MIMO thing. So what we understood from this is the diversity is the way to go. So we should not be looking alike. We should be looking for the how different it can be. So I feel that is the way. That is the way you are trying to means. That is the way MIMO should lead to. I have many comments on this call chat window. I can see that one, but we'll take. Maybe in the meantime, I think our chair, Mr. Puneet, also is there. So, Puneet, you are there. Can you just a few words from you before we take up the question and answer? And in the meantime, I'll just tell other participants to type out the question and answer in the chat window. Puneet, can you, if you are there, can you?
Dr. Chandrakant, thank you.
Please a little louder.
Yeah.
Okay. Now it is better.
I think little bit more.
One second.
Not audible yet.
Now it is better.
Yeah. Go ahead.
Yeah.
Okay. Thank you. Thank you, Dr. Chandrakant, and thank you, Dr. Devdeep, for accepting our invitation and delivering a wonderful talk on 5G.
Puneet sir, still it's like little bit not audible actually.
I don't know. I think it is a network issue.
Sometimes it's becoming clearer. Sometimes it's fading away.
No issues. Just I wanted to say thank you very much for accepting our invitation and delivering a wonderful talk on 5G.
It's my pleasure, sir. Thanks.
Related things, because it is a hot topic now, and most of the time when people have opportunity to listen about 5G, they are all related with communication side rather than antenna side. This is something really different, and that's why we have seen what Dr. Chandrakant has told, more than 150 participants, because you have covered the aspect of income as well as antenna, where this spatial diversity and all those things are very important and vital role. So thank you very much, and we would like to have you again at some point of time when we will discuss more about 5G. Dr. Chandrakant, you can take forward in proceedings now on.
Actually, I'm still, still not
For
audible.
your always encouraging words and being present in this talk. It means a lot to all of us. And to come with the question and answer. So there are quite a few appreciation of course, those things I'm not going to read out. Nice lectures and well thought out from the very beginning to the development of this one. So there are some general questions that has come. So first one is if somebody wants to start the research on massive MIMO sort of system or something they want to develop, what sort of infrastructure or what sort of things they need? because you must have seen many of the labs, so you have an idea. So I want to get a feel of it.
Yeah. I think this is a very like good question in the sense that we are presently, if you see the way the 5G testbed project in IIC or involved with other institutes is going on, that we are trying to look into building this indigenous passive MIMO testbed. So I went through some of the literature on that, and because I just the way I found the different papers, and I'd like to say that read that particular paper on the Lund University Massive MIMO testbed. So it actually has a list of the various components, like beyond, apart from the standard antenna fabrication thing, what other kind of things, what kind of specifications of the software defined radio, or what kind of switches and other back-end equipment we would need. Because it's not, the story does not, will not end by simply making the massive MIMO system. Like if we make a certain kind of antenna assembly, we need to actually put it in a complete combined system and a test bed, you can say, and we need to measure the various data rates or the signal to interference noise ratio, SINR kind of things. So those list of equipment, that open access paper it is, 100 element massive MIMO test bed, that is actually containing the list. So it will be better if the person who has asked the question refer to that paper. It has the complete description.
So you are referring to that paper from the Lund University. So
Lund University, yeah.
So then next question, it comes from another this one. Uh, uh, how to measure the ECC, envelope correlation coefficient in MIMO antenna?
Yeah. This is also, I think, this is a very common question that arises with all of us who started working on this MIMO antenna topic, because all the papers show the ECC, but very few papers will discuss about the measurement techniques. So one particular thing that I like to say, that measuring the envelope correlation coefficient between two antennas in practice would involve the measurement of 3D radiation patterns, and in terms of not only the pattern, say the amplitude part, but also the phase part, because the formula for obtaining the ECC is for a general case that will involve the complex 3D far field pattern. So if there is an equipment that is being able to measure the 3D radiation pattern from the antenna, when I at the end of my during my end of my PhD, IIT Kanpur procured one such instrument, so it is there in their anechoic chamber. So 3D radiation pattern measurement is very important, and going through all those things that can like, once the pattern is there, then the rest of the thing is just processing using the incoming wave. Another thing is, well, if we are dealing with a very general way, like a uniform propagation environment kind of scenario, then the S parameter based formula, it is also available in the literature, and to measure the ECC using the S parameter based formula, it is just the complex S parameters you need to find out. But it should be used with caution, because it is not the general formula. The general formula involves the incoming probability distribution and all the like statistical parameters also from the channel. So to do that, it is important to measure the complex 3D radiation patterns.
Okay, so in a nutshell, you have to capture 3D radiation pattern with magnitude and phase. Is it correct?
Yeah, exactly.
Rest is the computation.
What I could not follow.
Means if you capture the 3D radiation pattern with magnitude and phase, then the rest of the things can be calculated.
Yeah, you're right. Exactly. Yeah.
The next one, student is asking to start research on MIMO sort of device. What are the basic mathematical background, or means it's a very mathematics involved, as he could see from your vision. So what type of vision is required?
I would like to say that one thing, if somebody is interested in the design part of the MIMO antenna, then probably not too much mathematics is required, because MIMO antenna design actually involves the placement of various antenna elements, optimizing them to find out their S parameters and the proper radiation pattern, all those things. So that typical antenna engineer can solve. But if one tries to do some more like system oriented research, so I would like to suggest that person that probably some courses on the advanced signal processing. There were courses offered in IIT Kanpur. I fortunately did one of that. So those kind of things that will give some idea about the matrix kind of processing, because if you find the mathematical part in the MIMO processing will involve some like starting from the singular value decomposition to some of the advanced techniques that I represented in the end, like this combining the the Monte Carlo simulation and combining the Karhunen-Loeve model. So those kind of things, some communication courses need to be done. But again, I will repeat that if the objective is to design the MIMO antennas, not too much mathematics is required.
Okay, okay. Now another question they're asking in how to minimize the mutual induction, mutual coupling between
Yeah,
antennas.
between two antennas. Yeah, this is I think this is a very like a general question, and there are several ways to do that. Like if one way is to you can using mutual coupling is just to ensure that, well, when one antenna is excited, the current must not be exciting the other antenna in a way that there is some signal. So you can use, there is a popular technique known as the neutralization lines. Neutralization lines can be used. Then defected ground structure or some electromagnetic band gap structure, all those things can be used. One important thing to notice is if we just use the polarization diversity, like two orthogonally polarized elements in very close proximity, there also we will have basically very low kind of port to port coupling between the antennas. So there are various review papers and various techniques. So yeah.
Okay, then another general questions that is being asked by one of the faculties that where do you see the next 10 years down the line this research is leading to?
uh,
Step
I
aspect.
yeah. Yeah, well, this is I think I am too like I'm still not that much experienced to be that kind of a visionary, but what I am seeing that in there is this recent trend on the like software controlled intelligent surfaces. That is one of the, like I mentioned in the future scope also. So as I talked about that, we are trying to use, or we are trying to like minimize the use of our resources, and we are trying to get optimum system performance. So there are several aspects are coming up. So one such topic is people are thinking about a smart wireless kind of system where we can, instead of using these repeaters or the other things, people can control some of the elements or some of the periodic structures placed in the walls or something. So with very less power, they can actually redirect the beams and do some kind of smart communication. So this is a very exciting new topic that is going on. And definitely, as I discussed, that the ultimately when we are talking about the information exchange between the two things, there are certain ways, like we have tried to find out. We already have these ways of video conferencing and stuff like that. People are looking into augmented reality and all those stuff. So there are very much things that are available in the sci-fi movies now, and but might be some of the realized things in future. So yeah, future is exciting. And one more thing, I think in the present context, I have to add that the way this scenario with the coronavirus and all those things are going on. So I think thinking about it is very paramount importance to think about the how the healthcare or the research on that should be like beefed upon, or we can just think that how to increase the amount of research that is going on there. So that is one another important topic I feel that should be there in the next few years. And definitely space is there. Space science is already progressing. That is a separate topic. I will not probably talk much about that. Yeah.
Uh, Good. That lead to another question that has been posed, very fast question rather, in continuation to your question. That is there any relation do you see, or have you come across with this corona related thing and 5G communication system?
Well, I think to be honest, I discussed with many of my senior colleagues and other known people. So most of them, I share their opinion that this is probably not scientifically proved, and there is no as such relation. One of the important thing to notice is that the virus and all those things, initially I think some there was some suggestion that maybe the countries where 5G is implemented, their coronavirus is more. But I think that was way back. After 2 to 3 months, now we are finding that the countries where 5G is not there still, they are also having significant amount of coronavirus infection. And if you see that the virus dimension and the frequency range that we are talking about, the effective wavelength there, so there is no comparison. And another point that is naturally comes up is that whether there is some kind of radiation hazard or all those things involved. Well, they are also like the idea of using these multiple antenna system or to do all those things is to, as I mentioned in the beginning of my talk, that we want to reduce that nobody wants to increase the existing power level. People want to reduce that, and that is why we are using all those signal processing and all those things to actually come up with the better data rate even at the low signal to noise ratio. So I don't think that there is any such issue to be alarmed, especially the relation between the coronavirus and 5G. I don't think that there is any connection.
Thank you. There are many questions that were floating in now also. So I just concluded that small this one the students must have posted this one. He has asked that whether knowledge in MATLAB is very much required to work in MIMO.
I would suggest yes, because there are once we just I mentioned for the example for the ECC calculation that you need to find out the patterns, and there it will be better if you can put the patterns in some MATLAB code and write your own algorithm to find out the correlation coefficient. So that is just one example. Another thing is right now the MATLAB is having this RF toolbox, and if that is available, then it is also very much important from an RF engineer perspective that it can actually I had discussion with Dr. Said, who is my close collaborator, that he gives his students some problems in the MATLAB toolbox. So complete system can be designed, the scattering channel model or the ray tracing model, everything can be put into there along with the antenna properties. So if somebody knows MATLAB very well, then he can probably integrate the concept of antennas with the concept of communication and do a proper system oriented research. So yeah, MATLAB is definitely important.
Okay, then, Dr. Sarkar, with that I'll close because there are many questions that are floating in, but we are beyond time, and thanks for the nice lecture.
Yeah, thank you for the hosting.
I'll
And
request Kirti to formally propose a vote of thanks and close the session.
okay.
Thank you, Dr. Chandrakant. Well, I can see the number of questions that are coming still now. So that shows how interesting the talk had been today. You clearly, elaborately explained everything starting from evolution and the mathematics involved. So the demography of the audience which we had today had consisted of students, academicians, industry people. So your talk was nicely catered to all of them, and I think everyone had something to take away from this. And most important of all, I would like to thank IEEE Bangalore section for providing all their resources and help us arrange this talk. We hope to organize more amazing lectures like this, and thank you all the participants for their interesting questions and their interactions. And I hope to see you all in the forthcoming lectures. Thank you all once again. Stay safe and good night.
Thank you.
Okay, Dr. Sarkar, good night.
Yeah, good night.
Forward to meeting you some forum maybe physically.
Yeah, sure. We'll meet. Yeah, thank you once again.
Bye-bye, all the participants too.
Yeah, thanks to all the participants who patiently listened to all the talk, and I look forward to meet with many of you in near future. Thank you once again.